Greetings, environmental epidemiology students. So I'm probably wondering why Chris Farley from Bill Swirsky Superfans is up there on your screen. And the reason is because we're discussing confounding, and I needed a good picture of a heart attack, and that seemed to be the best one. So anyways, the flip phone and the heart attack relationship. Why would I bring this up? Well, the main reason why I bring this up is because if a person were to create a speculation that flip phones were associated with heart attacks, you know what? They would probably find that people who have flip phones are more likely to have a heart attack than people who have smartphones. Why? Why are flip phone users more at risk for heart attacks than people with smartphones? Well, the reason is simple. It's confounding. Confounding is a situation where a variable of interest, sometimes even unknown, is associated with the disease outcome and the exposure of interest. So, if the exposure of interest is a flip phone, and the disease outcome of interest is the heart attack, what's the confounding variable? And the confounding variable here is age. Younger people in general are more likely to have iPhones or some other type of smartphone, a Samsung smartphone or something, rather than a Samsung flip phone or any type of flip phone. So this relationship is confounded. It's not that the flip phone causes the heart attack, it's the age factor that probably is associated with the heart attack. It's the lifetime of inflammation and diet and genetic factors that add up to things over a lifetime. It's age that puts a person at greater risk. And then it is the flip phone up here that is associated with both age and the outcome. So, in confounding, a confounding variable is something that is linked to the exposure of interest. There's an association there, and there is a relationship between the exposure and the disease, and the confounder is also related. So, this thing called a confounding variable, it confounds our ability to show the exposure's relationship with the disease. It makes it harder to see this. Sometimes it even blocks this relationship. Sometimes it makes this relationship stronger. So there's a lot of things that go on. But in order to fully appreciate the benefit, not the benefit, but in order to fully appreciate the impact of the confounder, to know its benefit or its harm to your relationship that you're trying to figure out, you have to probably look for it. Here's an example. If you were trying to see if there's a relationship between coal mining and lung cancer, or coal mining and COPD, chronic obstructive pulmonary disease. If you were trying to see this relationship, it's going to be harder to tell unless you adjust for smoking. A lawyer is going to say, if you're representing maybe the coal miners who've got lung cancer or who've got COPD, or who have black lung disease, that they're trying to say is COPD, and you come in and you say, you know, I worked in that mine for 23 years, or my father worked in that mine for X number of years, and he was exposed to the worst of the worst, and now he's got lung cancer. What's the coal company's attorney's going to say? Or any attorney, or any medical doctor, or any epidemiologist? Well, did your father or the guy who's mined, did he smoke? Because smoking is associated with the lung condition as well. So this relationship between here and here is confounded by smoking because smoking is associated with the disease. So when we do studies, whether they be cross-sectional, case control, cohort, or whatever, we have to be prepared to adjust for confounding. So you need data on your cases and your controls that doesn't just ask about what you think is the relationship of interest. It also asked about known confounding variables like age, gender, and smoking. So when you look at the impact of smoking and you see, yes, this actually makes the minor even more likely. It actually makes it worse. That's an important finding. So you could say, yes, smoking causes COPD. However, being a minor and smoking made their likelihood of having COPD even worse. And if you adjust for smoking, you may find out that mining by itself also is associated with the outcome of interest. There are statistical approaches that are out there that we're not going to go into too much detail on. I'll mention briefly here in a few minutes that allow you the ability to see whether or not something is confounding the association. But you can't check to see if it's confounding an association unless you actually measure what you're trying to look for. So you can't assess the impact of smoking on lung cancer among coal miners unless you actually asked about smoking or know about smoking for those people. So in this example here, we're going to look at how we might assess confounding in a example study. These are not real data. These are ones that I fake created. And I've got my phone here in my hand because I'm going to use a calculator here to do some calculations. And you can do these calculations too. Say we're wanting to look at the relationship between coffee and heart attack. There are people that have said, oh, coffee causes heart attacks. It raises the caffeine levels in the body. That causes heart attacks and raises stress levels and all that. So you do the study, and here's the results you get. Coffee drinkers and heart attack, non-coffee drinkers, heart attack. This is D bar. Heart attack's disease, no heart attacks, D bar, no disease. Coffee drinkers is exposure. Not coffee drinkers is non-exposed. We've got our 2x2 table right here. So how are we going to do our odds ratio? A times D over B times C. So what do we get? 90 times 90 is 8,100. 8,100 is divided by 60 times 60, or 3,600. 8,100 divided by 3,600 equals 2.25. All right, that equaled 2.25. So in our little example here, the odds of heart attack were 2.25 times greater among coffee drinkers than not coffee drinkers. Make sense? So that's our initial assumption. Have we adjusted for anything? Like we haven't looked at age, we haven't looked at smoking. So let's look at the impact of smoking. So our odds ratio was 2.25 here. We have 150 people with heart attacks, 150 people without a heart attack. We have 150 coffee drinkers. We have 150 non-coffee drinkers. We've got the same people. We're just going to stratify them now. So how many people do we have heart attack over here? This amount here totals to what? Among the heart attack people. Among heart attack people. Over here, heart attacks, 150. Here, we have 100 smokers who had heart attacks. Here, we had 50 non-smokers. The heart attack people add up to 150. It's these people right here. stratified into smokers and non-smokers. And then you've got the non-heart attack people, 50 and 100. They're all there. The coffee drinkers. How many people were coffee drinkers? We had 150 coffee drinkers. 120 plus 30. They're all there. We've just stratified it. We've taken this 2x2 table and made it into two different 2x2 tables. We're going to look at the odds ratio for heart attack among the smokers who drink coffee or don't, and we're going to look at the odds ratio for the non-smokers. So when we do that, what do we get? We can do our 2x2 table for over here. The 2x2 table here is 80 times 10 is 800. Divided by 40 times 20, that's 800. 800 over 800 means among the smokers, there was no effect of drinking coffee on heart attack. The odds ratio was 1.0. There was no effect. What about here in the non-smokers? 10 times 80 is 80 over 20 times 40. There was no effect. Did you see that? 1.0 is the odds ratio here. 1.0 is the odds ratio here. But when we looked at it in the big picture, before we stratified or adjusted for smoking, what did we see? We had an odds ratio of 2.25. Now it's 1.0 and 1.0. The odds ratio has changed 125% for the smokers. It has changed 125% for the non-smokers. It went from 2.25 to 1.0. It went from 2.25 to 1.0 for the non-smokers as well. So that change in the odds ratio, not just greater than 10 or 15%, but that's like huge change. Changed like 125%. That's clear evidence of confounding. If we were to cut this differently, and instead of look at heart attack and coffee, we look at heart attack and smoking, or we could do that here. You could look at heart attack among the smokers and heart attack among the non-smokers. What you would end up finding out is that here we've got a lot more heart disease among the people who are smokers. In fact, if you were to stratify it all kinds of different ways, I'm not going to have you ever do that in here, but if you were to go through and take those numbers and re-stratify them, you would find out that the odds ratio for smoking and coffee is 16-fold. So those two exposures are highly related in this little sample. And smoking was actually associated with heart attacks. 4-fold increased odds in heart attacks among the smokers. So coffee and heart attack, 2.25. Smoking and heart attack, 4.0. Neither of those are adjusted right now. But anyways, you have clear evidence that there was confounding. So what made it confounding? What makes something have confounding? So a confounding variable is one that alters your kind of belief or your study, where you're trying to look at an exposure and an outcome. And if the exposure is coffee consumption and heart attack, and you had an odds ratio of 2.25, but now the exposure, that is the confounding variable, whatever it might be, or the presence of the confounding variable, the age, or in this case, smoking, if that changes the exposure relationship with the disease by more than like 15%. So if it goes from an odds ratio of like 2.25 to 2.5, that's a 25% jump in the odds ratio. That's confounding. If it goes from 2.25 down to 1.0, that's a 125% change. It can actually change when you stratify for one group and not the other. It could go from 2.25 in one group to 1.0 in the stratified group and stay 2.25 in the other group. That's still evidence of confounding. If just one stratification moves it more than 15%, we've got evidence that confounding is present. There are other ways with statistics to do more, but we're just keeping it based off of the most simple designs. So what are the three main sources of confounding in epidemiological studies? Well, the main sources are age, gender, smoking status, and those are the biggies. What are some other ones? Well, you could imagine them. Income or socioeconomic status, race or ethnicity. Those are a few of the major ones. Alcohol consumption, drug use, maybe underlying genetic factors, occupation. There's a lot of these that are out there. How may we control for confounding in case control studies? So there are a few different ways you can do that. One of them is limit who's in your study. Just limit it to smokers or limit it to non-smokers. If you do limit it to smokers or non-smokers, that means you can't assess the effect of smoking, but those are things you can do. All right, I'm not showing you that. So you should be able to construct 2x2 tables. You should be familiar with the different misclassification biases, all that stuff. What are the main sources of confounding? We've kind of covered all this. All right, so the last bit of the case control studies, and we're going to cover case crossover studies really quickly. We should know these review questions already. Here in this example, you do a case control study on asbestos exposure and mesothelioma. When comparing the asbestos exposure to the presence of mesothelioma, we see an odds ratio of 4.0. Okay, so more asbestos, more mesothelioma. When stratifying or controlling for smoking, the odds ratio for the smokers is 1.0 and for the non-smokers is 1.0. So is smoking a confounding variable? So when we adjust for smoking, there's no relationship between asbestos and mesothelioma in this example, and there's no relationship between asbestos and mesothelioma for the non-smokers. But it was 4.0, now it goes to 1.0 and 1.0. Is there a confounding? Absolutely. How much did this odds ratio change? It went from 4.0 to 1.0. That's 3.0 times 100. 300% change in the odds ratio. Definitely evidence of confounding. What about here? In this example that's on your screen right now, we've got 4.0 in the asbestos and mesothelioma crude odds ratio. The stratified odds ratios, when we adjust for smoking, shows the same effect, 4.0. And in this one, 4.0. There was no change in the odds ratio. So is smoking a confounding variable in this example? Usually it's a confounding variable, but in this example it's not. All right, say you see an adjusted odds ratio in a paper that looks like that. You should hopefully immediately recognize that that's statistically significant because one's not included. It's pretty easy. The p-value would be less than 0.05. All right, we're going to do the case crossover example really quick. So there is a unique type of case control study called the case crossover. And in the case crossover studies, the control group is the actual same human beings that are the cases. And these are commonly used studies, especially with air quality. So here are our cases, the disease group. Here are our controls, the non-disease group. These people had a heart attack right now, recent. These people are the same human beings, but they didn't have a heart attack 7 days earlier. So they call this case crossover. And in this example, a day before or the day of the heart attack, within the 24 hours of them having their heart attack, there was a smog alert for these people. And the other people at the hospital over different days, the day before they had their heart attack, 40 of them had no smog alert. When we go to the people that had the heart attack and we look at the air quality 7 days before, among these 60, they go 7 days before and no smog alert. Among these people, or among all these people, they go 7 days before, no smog alert. Here, smog alert days for both days. Here, no smog alert. You can then do the cross product ratio or the odds ratio and do 60 times 80. Get your 4,800, divide it by 20 times 40 over 800, get the odds ratio of 6.0. There are other studies that are like this. Right now, there are studies that are out there that are doing this with COVID-19 infection and air quality, trying to figure out the day that they got COVID-19, also those trying to figure out the day that they died of it, and what was the air quality like in China. There's some reason to believe that when the air quality is in the tank or it's miserable, people are more likely to have respiratory conditions and be more vulnerable to being infected. So they would do 1 day before they were presumably infected, or maybe 3 or 4 days before they show clinical signs or symptoms, and look at the air quality. And then they go 7 days before they were infected and look at the air quality. So those are different things that are out there. Why are case control studies good? Why are they good? The main reason is they're good for studying rare diseases. So if there's only like 50 people in the world with the disease, then you're not going to do a cross-sectional study and try to find those people. You're going to go to the sick people, and you're going to find them, and you're going to match them up with other people that are kind of like them. Maybe siblings, maybe people at the same hospital. Make sense? Also, if the disease is rare, like it's an occupational disease, and you got 40 people at a work or at a job site that got some horrible disease, and it's really uncommon in the rest of the world, you then need to compare them to other people that they may work with to figure out why they got the disease and the other people didn't. Was it where they were working at or whatever? So these are really good for studying rare diseases. They don't require as much money as like a cohort design. And you can get an odds ratio, which is a pretty good estimate of risk when a disease is rare. We're going to do risk ratios in the next set of videos with cohort studies. Risk ratios and odds ratios, true risk and odds are almost the exact same when a disease is rare. But when a disease is common, there can be big differences between the odds ratio and the risk ratio in terms of whether the odds are actually predicting the risk. But when it's rare, the odds ratio and risk ratio are essentially the same. Some weaknesses. Case control study designs. You've got your cases and your controls, and that's all you can look at. You have a harder time proving the sequence of events. Prevalence incidence bias still exists. You got cancer, were you ever exposed to this? Well, 20 years ago I was exposed to it. Well, when did the cancer start? We don't know that. Cohort studies, we know when they started. We're doing monitoring throughout their life, and we're better at assessing the sequence of events, which is better for causal. The potential for recall and interviewer bias is higher. So if you're trying to ask people about their previous exposures, unless you're using patient charts or work records for a case control design, if you're using interviews of cases and interviews of controls, there's the potential for bias where the people who are sick remember more or harbor a grudge and are willing to divulge more. Selection bias is also possible. So Who do you set as your controls? Paying attention to the control group is something we're worried about. And in a case control design, if you're interviewing people, you can't interview people who have died as easily, maybe their spouses, but those are the big issues. So you should be able to know the difference between odds ratios and stratified odds ratios, the crude ones and the stratified, and be able to tell which one or if it's got confounding. More than a 15% change is evidence of confounding. Going from like 1.2 to 2.0 on an odds ratio in a stratified group, 1.2 in the big group to 2.2 in the stratified group, that's an odds ratio of 1 difference, which is equal to 1 times 100. That's 100% difference. So that would be evidence of confounding. All right. So I don't want to spend too much time because these review questions, you'll have a chance to do them on your own with some quizzes. So we'll have an exam on this big section. I'm thinking about when to do that exam and how to best do it. I'll follow up with you all in email form. If you have questions about these videos, or if you're having challenges or any struggles within your classes, you can always reach out to me, jason.marion@eku.edu, or you can text me, and I'll do my best to respond back quickly. It's been a rough week for grant applications. Had a nice there have been some long ones. So this next week, more grading should be able to get done. My life gets a lot better after April 15th. So I hope that this has been informative, this video, and I look forward to interacting with you more the best that we can in this world that we're in. Thank you, and I hope this has been rewarding.